Okay, so we're reviewing stuff on linear independence, basis, and dimension, which will be on demonstration 2, which will open up over the spring break, and also is the subject of some of the questions on assignment 4. And so this week we don't have any new material; we're just reviewing other material. So let us start. We're just working some problems now. Let's do one with, let's say, we have a question of, let's take a space. Let's say this space, in which we have it's a set of it's this set P. Just give it a regular P. So we have a set P, and it's inside the 3 component column vectors, but there's 2 constraints. These 2 constraints form a linear system. So one of the first goals would be to find, or one question we ask about this is find a basis for P. Okay.
And linear possibility.
Excuse me?
Is it linear possibility?
For
in the equation above?
Yes.
3y plus 4z, or
this is, oh yes, you're right. 3y plus 4y wouldn't make much sense, would it? There, okay. So the idea is that to find what a basis is, a basis, it is to find a basis, we have to find a set of vectors which is 1 linearly independent, and 2 spans the space, spans P, right? So because we're trying to write P as a span. Now, the technique that we're doing is we're going to solve the linear system for the free variables in terms for the leading variables in terms of the free variables, and then eliminate the leading variables from here. That'll leave us with an unconstrained variable or a constant vector, which will just be, it'll be a vector space, presumably. Okay, well, let's try that and see. So here's our here's our linear system. And let me see. What I want to do is I'm going to change the linear system slightly. I'm going to change my coefficients at the risk of ruining your notes. Okay. But this is a attempt. We'll see if this enables us to avoid fractions. Well, this is in, this is in echelon form already, because there's nothing under the x component here. And just to be clear, if we wrote this as the augmented matrix, it would be 1, 3, 2, 0, 0, 3, 4, 0. And you can see clearly then that this is in this or this is in echelon form. Okay, so what it means is that X and Y are leading, but all the variables that are not leading are free, so Z is free. So we want to solve these equations here for Y in terms of Z and X in terms of Z. So we can just do back substitution here and write away solving the second equation to get Y equals minus 4/3 Z, right? And then we can use that in the first equation to get X plus 3 times minus 4/3 Z. This is why I actually changed this from 3 to 2, because I saw this was going to put a 3 in the denominator. And if I put a 3 up here for the Y, the 3's would cancel. We wouldn't have any fractions. So that's why I changed this up here to in the substitution, so these 3's would cancel. That's just a convenience. That's not relevant to this. Okay, so we have X plus 3 times Y using a result from equation 2 plus 2Z equals 0. And then you can see that this is going to be minus 4Z plus 2Z is going to be minus 2Z. So X is going to equal 2Z will be the solution. So we have here expressions. X equals 2Z, Y equals minus 4/3 Z, which so we solve for the leading variables X and Y in terms of the free variable Z. And then we want to go back to our expression here. And then the point is that this is the set of all X, Y's, and Z's such that X, Y, and Z are solutions of this linear system. But that's what this notation means. It says this set P is all of these things such that X, Y, and Z solve the linear system. Well, if I choose any X, Y, and Z, so this is true, they solve the linear system because this is the whole point of Gauss's method. So we can rewrite P as, I'm going to do it in 2 steps, X, Y, Z, such that X equals 2Z and Y equals minus 4/3 Z for any Z, for any real number Z. Okay? And the point of, so we've used Gauss's method to solve for leading in terms of free. And the idea then is that allows us to parameterize the solutions by removing the leading variables. So we can write P as 2Z, because that's X up here, 2Z, and Y is minus 4/3 Z. That's using the expression Y, and then Z for the third component, such that when we've gotten rid of these equations by plugging in and removing X and Y, so it remains just implicitly for any Z member of R. Now, so then I just factor out the Z here. This is like this equals Z times 2 minus 4/3 and 1 such that Z is a member of R. So this shows that P equals the span of the set 2 minus 4/3 1. Because what a span is you give a set here. It only has one vector, but the point is that a span is the set of all linear combinations of the vectors in this set. Well, this is the set of all linear combinations of this vector. It's all the multiples of this vector. So therefore, we've written P as a span. Now, so we know that this vector spans the space, but now any vector by itself is linearly independent. So a single vector, a single vector is linearly independent. And we could just, although it's a little pedantic, we could go through and ask, why is it linearly independent? And we could apply, because it's not a linear combination of any other vectors in the set, and we could apply that test. The test is, suppose, this is a little bit pedantic because sort of is obvious, we could suppose that A times 2 minus 4/3 1 equals 0, 0, 0. Now, if this is linearly independent, this should imply that A equals 0. That's the linear independence test. Okay, well, clearly, this just gives me three equations. 2 times A is 0, minus 4/3 A is 0, and 1 times A is 0. So clearly, we have A equals 0. So S equals 2 minus 4/3 1 is linearly independent. Since it's linearly independent and it spans the space, we know that this is a basis. Okay, well, there's one example that gets this idea, and let's go back and look at this coefficient matrix here. So this is the coefficient matrix of the linear system that's in this set here, 1, 3, 2, 0, 3, 4. So let's look at this matrix M equals, and I've forgotten already, 1, 3, 2, 0, 3, 4. 1, 3, 2, 0, 3, 4. Here's the coefficient matrix. Now, since it's already in echelon form, we can ask, well, what's row space? There's a special space associated with any matrix. So that row space equals the span of the rows. So row space is going to equal A times, well, we could use, A times 1, 3, 2. Now, this is a row vector. It's not, there's no commas in here. This is just a row vector. Plus B times 0, 3, 4 equals, well, rows, it's the string, all the linear combinations of the rows such that A and B are members of R. So that's row space, right? Just the linear combinations of the rows where we take each row as a vector. So we can write, this is the row space of M. Now, and we can also say, you can see the dimension of this space, a basis for row space. Since this is an echelon form, the point of echelon form is that the row, or one feature is that the row space here is these vectors are linearly independent, in the sense that if I set this linear combination to 0, that would force A and B to be 0. There's no way to write one as a multiple of the other. And you can see it intuitively, because if I want to write this vector, 1 through 2, as a multiple of this one, there's no way to multiply 0 by a number to get 1. Whatever I got with a 3 and I could somehow put a number in front of this one to get maybe this 3, 2 to be 3, 4, somehow like that. But there's no way to get this one. So we know that this is linearly independent. So therefore, a basis for row space would be this set here. Because it's, by definition, it spans the space. Because it's an echelon form, it's linearly independent basis for row space. And therefore, by definition, we say the dimension of a space is equals number of vectors in any basis. Okay, so here the dimension of the row space of M equals 2, because there's 2 vectors in a basis. So these are just definitions of words, right? We have the number of vectors in a basis, it's 2 here, so we call that the dimension of the row space. We can take then we can also, continuing our survey of terms, we can also take the same matrix. Let me repeat this matrix here. M equals 1, 3, 2, 3, 4. And so what's the column space of M? The column space of M equals the span of all the columns, just like the row space is the span of all the
So the dimension for this is 2.
So there's the column space. Now what you're thinking of right away is that there's a theorem that says that the dimension of the column space should equal the dimension of the row space, but it looks like here that something's going on, right? That we've got 3 vectors here. So if this was a basis, 1, 0, 3, 3, we know that 1, 0, 3, 3, and 2, 4 span the space, but are they linearly independent? So are these vectors linearly independent? Okay, well, so we're talking about these vectors here. This set here, 1, 0, 3, 3, and 2, 4. Okay, well, so that's the same as asking, well, could we find a basis for column space, right? Well, we found a basis for row space with Gauss's method. So if we could use Gauss's method to these columns, we could do that. Now, the way to do that is to take this coefficient matrix, right? 1, 0, 3, 3, 2, 4, and take its transpose. A transpose interchanges rows and columns. So the first row becomes the first column. The second row becomes the second column. Okay. So now the idea is that we can use Gauss's method now. Okay.
I think that writing the vectors, I think it's 1, 0, 2, 3, 2.
Oh, yes, I was wondering about that. So I was just misquoting the vector here, so that will change things here. Okay. Okay, so there's the transpose. Now, so we do is we apply Gauss's method to this transpose. Now, it's not an echelon form, so we have to make some row operations to bring it to echelon form. And we could do -2 row 1 plus row 2 because we want to eliminate this 2. We could also do -3 row 1 plus row 3 to eliminate the 3 here. And we can put these 2 together because they don't interfere. This first row operation changes row 2. The second one changes row 3. So we can just sort of do them independently. They don't interfere with each other. So we can sort of combine them there. So it doesn't change row 1. This operation, -2 times 1 is plus -2 is 0. And -2 times 0 plus 3 is just 3. Then -3 times 1 is 0. And -3 times 0 is 0 plus 4 is 4. So we get that. And that's enabled us to clear to clear this first column. So we're almost in echelon form. We just have to get rid of this one here. And so we can do is we can say minus 4/3 row 2 plus row 3. Make it write smaller here. 1, 0. It isn't going to change the 0, 3, but it is going to multiply minus 4/3 times 3 is minus 4. Minus 4 plus 4 is 0. So I have a 0. So now it's an echelon form, right? Now, the claim is that once it's an echelon form, the row space here, this is the transpose, this row space here is linearly independent, and the non-zero rows form a basis. So therefore, we know what we can do is we can see that 1, 0 and 0, 3 are linearly independent. So what we do is we transpose back. This is what we do. We transpose back, and the first column becomes the first row, and the second column becomes the second row, okay? And then we see that, okay, the columns here, the non-zero columns form a basis, because 0, 0, this is not linearly independent, so we can just remove the 0 vector, because so as a result, the basis for column space is based on 1, 0, 0, 3, we could say. And so, and now just one thing, a basis is always a basis is a sequence. I've been talking about a set. We do need to find a linearly independent set, but a basis, a basis is a sequence. So what we say is so there's two actual bases we can get for this. We could have basis 1 equals, and we use angle brackets here to just indicate that we're actually choosing an order, right? So there's one basis, and the second basis we could obviously get would be just choose the other order. So those are both bases for column space. So we can, so the idea is we can use the same method we use to find a basis for row space for column space if we do this transpose, use Gauss's method and transpose back. I haven't really justified exactly why this all works, but it does. Okay, now the point is here, we can see that the dimension of column space of M now is equal to 2, right? Which matches the dimension of row space. So now these dimension of row space, dimension of column space are given special names. The rank of M is a name for, well, there's the row rank is the dimension of row space, and the column rank of M is the dimension of column space. But the point is that there's a theorem that says these two spaces are always the same. So the row rank and the column rank are equal. So we just say the rank of M is either one of these. So the rank of M here equals 2. So that's the basic. So if you wanted to find the rank of a matrix, you could find either the rank of the columns or the rank of the rows, whichever one was easier. And because they're both going to be the same value. And if you see, if the matrices are different sizes like this, and the number of rows is like the number of columns, you can see that the rank can't be larger than the number of rows, right? But that means if this was like 2 by 20, we could have 20 column vectors, right? But that means they'd all be linearly dependent, because the rank could at most be 2. And so and you can see what happens here is if this is a two-dimensional space, it's only good, it's like you can see 1, 0 and 0, 1 would be the standard basis, and you could write all the vectors in all two-dimensional vectors in terms of that space. So, okay, so there's something going on here that with this is all a terminology. Okay, so let me